Okay, ready? Okay. Okay, let's start. This course is about MATLAB control system toolbox. And this course consists of two parts. I'm going to take part in only first part. The second part is by yourself. So you pick up one simple problem and work on controller design using the code that I explained today. So in the second half, we ask the help from Jesus, how to write homeworks so that we can put everything on the web. And another purpose of this lecture is to make some materials educational to everybody. So everybody picks up different systems and problem, and in the web, as Jesus will explain, you explain how to build a model, what's the importance of the problem, and design the controller and do simulation and show the results. And then everybody reads everybody else's web page, and then we can study each other. Okay, this is another purpose. And here I'm going to just show the simple theoretical part that I already explained in a couple of weeks ago. So this is just a recap. This is system, linear. But you have to, if your system is nonlinear or if your system is infinite, then deriving this part takes some time. But anyway, suppose we have this finite dimensional linear system, and we want to minimize this cost function from t0 to t infinity. This infinity is important because to minimize this value, this part and this part has to go to 0. So automatically, by solving this problem, you stabilize this system. And in engineering, this stabilization is important. And this Q and R, symmetric, positive semi-definite, and positive definite. And the conditions imposed in our system is like this. AB is stabilizable. Okay, this C is different. QA is detectable. If Q is written as a product of C times C star times C, then CA is detectable, or QA is detectable. Then the solution for this optimal control problem is given by this feedback input. Input is the feedback, because this is just a constant matrices. And X is the state. So state is fed back and plugged into this U. And the overall system, we often say this is closed loop system, is autonomous. Autonomous system, and for any initial value x naught, the system, the closed loop system, the behavior of the closed loop system goes to 0 because we stabilize the system. And in this control, you have to compute this P. R is here, and B is from here, and P you have to compute. This is called the algebraic Riccati equation. And with this control, the cost is minimized, and the value of the minimum cost is this, given by this. This x naught is the initial condition. And moreover, this system will be asymptotically stabilized. Namely, this closed-loop matrix will be stable or Horowitz matrix. So this is a standard LQ control problem. And we're going to apply this to simple mechanical system, inverted pendulum. So this material is very standard in control engineering department, using this kind of mechanical system. Although this is nonlinear, we derive the system equation and find out equilibrium and linearize it and get A and B, and apply the algebraic Riccati equation and get the feedback control. So this is also explained a couple of weeks ago in my talk. And so this is the inverted pendulum, mass of the pendulum, and also mass of the cart, and your input acts on this cart. And this is a pivot so that this pendulum freely moves. And you have to derive the equations of motion. The standard way in engineering is to use the Lagrangian method. So to derive this Lagrangian, you have to compute the energy, kinetic energy of these systems, and potential energy. And the kinetic energy minus potential energy will be Lagrangian. I skip how to derive this, but this is sort of simple procedure using physics. And if we get this Lagrangian, the next step is to derive Lagrange's equations of motion. I did not write the formula of Lagrange's equation, but you have to do partial derivative of L with respect to X, with respect to theta. Theta is the angle. X is the position, horizontal position of the cart. And also the partial derivative of L with respect to X dot, the velocity of this cart, and also with respect to theta dot, angular velocity of the pendulum. And after computing this derivative, take total derivative with respect to t. Then you get two dots here, x2 dot, theta2 dot, and theta2 dot, x2 dot. And solve these two equations with respect to x2 dot and theta2 dot, like this. And then you introducing x1, which is x, x2, which is x dot, x3, theta, x4, theta dot, you get four-dimensional system. Like this. Okay, solve with respect to x2 dot and theta2 dot. And the nonlinear system you get looks like this. Okay, this is U. That's the input force acting on the cart. And because you solve these two equations, because of this inverse matrix, you get this kind of fraction in your system. So this looks quite nonlinear. So this is the nonlinear system we have to deal with. F depends on x and u. Qx. In this case, u is just a scalar, so I didn't include any r, just a u squared. Okay? And to get a linear system, you have to you have to set your equilibrium of interest, which is in this case the upright position. Downward position is also equilibrium, but we are not really interested in this downward position. We want to stabilize this pendulum upright and hold it by control. You have, I guess you have played with this kind of game when you're little. So we are trying to mimic this kind of game by this kind of control. So then the equilibrium will be x1, which is the position of card. So there is no specific position, so we set some specific value, which will be in the middle. And x2 is x dot. So this will be 0 at the equilibrium. And x3 was theta, so this will be 0 at the equilibrium. Theta 4 was theta dot, so this will be 0. So some value, okay, we can say this is 0 as well. 0, 0, 0, 0. That's the equilibrium. And also U has to be 0. Equilibrium means that this right-hand side has to be 0. Okay? So U also has to be 0, and all of these guys are 0. And at this place, we linearize this nonlinear system. Then we get this A matrix, B matrix. A is from the Jacobian matrix of F with respect to X. So this is 4 times 4 matrix. And B, oh no, this is completely wrong. This is F00. No, this is correct. This is correct. Because this is not a fine form. So take a derivative with respect to U and put 0, 0. That will be B matrix. And these B are same. So this is the derivation of model. And if we get this model, we just throw these data into MATLAB. Then MATLAB will compute the feedback control. So from now on, I will move on to MATLAB. So start up your MATLAB. And let me confirm the files you have. This is the file I prepared. 1, 2, 3, 4, 5, 6 files. And README is just a document explaining what all these files are. Okay? So this is my MATLAB. And open your editor and use first file, which is inverted penned model. So these are small, but I hope you can see. I'm using magnify. If you want, I can go 400%, which is better, but not so much information here. Which is better? 300? 400? Like this? This is better? Okay. So normally we start with clear all the memory. so that every time MATLAB don't get mixed up the data. So always at the beginning, run this clear all, and clear all the screen, CLC. And I'm going to use a symbolic math toolbox because this Lagrangian is a little complicated. And in engineering or mechanical engineering, much more complicated system has to be dealt with. In this pendulum, only two parts, which we call the 2 degrees of freedom mechanical system. But if we append other parts, then there will be 3 degrees of freedom, which will be 6-dimensional system. And the Lagrangian will be much more complicated. So derive Lagrangian carefully. Actually, you can use symbolic math toolbox to derive Lagrangian. Because Lagrangian is just the potential energy and the kinetic energy. So which part rotates around which point, and compute the moment of inertia, then you can automatically derive this Lagrangian. But I wrote here by myself. Okay, we start with this Lagrangian. And as I explained, this Lagrangian has to be differentiated with respect to x and x dot and theta dot. This gets quite complicated because lots of cosine and sine. So I use symbolic math toolbox. And one important thing or annoying thing of using this symbolic math computation is that they don't understand the chain rule. As I told you, we have to differentiate L with respect to x dot and theta dot. After that, we are going to take total derivative of that quantities with respect to t. And x and theta, x dot and theta dot, are function of t, so you have to apply chain rule. Otherwise, you don't get the x2 dot and the theta2 dot. To do that, you have to use a little bit of tricks. So that's why this part looks a little long. This part only computes the partial derivative of Lagrangian with respect to x, with respect to x dot, theta, theta dot. And after that, but I forgot important things. To use a symbolic math toolbox, you have to declare what is the symbol. So T is symbol. So write the sims T. By doing this, MATLAB understands T is a symbol. And X and dx, theta, theta, these are X and X dot and theta dot. These are also symbols. And M is a mass of cart. Lowercase m is the mass of the pendulum. L is the length of the pendulum. And G is the gravitation for constant. These are also constant for now. And these Lagrangian derivatives of Lagrangians should be symbols. So I declare these are all symbols. And define Lagrangian and take derivative. In this derivative, you have to sort of functionalize this x as a function of t, dx also a function of t, theta function of t, d theta also function of t, and the dl dx also function of function, dl dx dot is also function, and these four derivatives of Lagrangian has to be also function. And this diff means the command of differentiation in symbolic math toolbox. So after declaring x underbar f is a function of t, you can write this. So take derivative of this guy with respect to t. And write dx underbar f. And also we do the derivative with respect to t to theta and define theta dot. And these tricks are related to how to compute chain rules. So it's a little bit complicated. Not too much, but a little bit complicated. So anyways, let's run this program until up to here. Oh, this function is very important, very convenient. This is sort of a debug mode. So instead of running all these files, this MATLAB computation stops here. But still, in the memory, the computation, the result of this part will be saved in the memory. So by using this debug mode, you don't get annoyed all the result after this part, but you can see what is computed here. So, for example, I showed here the result of a derivative. You can see. For example, the last one is the derivative of Lagrangian with respect to theta dot. And that's this one, okay? And we are going to take derivative of this with respect to t. Then we will get the differentiation of, for example, x 2 times. So this will be, after taking total derivative, this will be x2 dot. To do this kind of things, I use the sort of a little bit of techniques. But basically, what I'm trying to do is just to do compute chain rule.
So,
yeah.
At this point, I think some people use automatic differentiation, right?
Yeah, yeah.
Is this somehow built in MATLAB?
Yeah, it's built in MATLAB. Yeah.
Because some people use it from outside, right? Like 8 ampere or no this, right? It's not. So when you use the algorithms to optimize based on ampere and IPO and all this, you are not calling to automatic differentiation tools that are outside MATLAB? Oh, I see. So this automatic differentiation tool of MATLAB is in the control toolbox or is in the general?
This is a symbolic math toolbox. Another toolbox. Yeah,
Which
yeah.
toolbox?
Symbolic math.
Symbolic math.
Yeah,
Okay.
yeah. So there are other this kind of softwares called Mathematica and Maple. They do the similar things.
And how do you call this command that computes the derivative? You can take an expression as huge as
Yeah,
you wish
yeah,
and
yeah.
ask for a derivative. And
Yes,
it will.
yes, yeah, yeah. It's possible. Yes.
Some people don't like this. Is there a drawback of Lagrangian differentiation? Anyone understood this?
What do you mean
Is there a
drawback?
drawback? Is there a negative effect? Does it always work?
Well, it gets complicated, but you can really do by hand, but they do that.
But it's great. And you can even use the derivative of the absolute value, right? And you will get something.
Phoenix uses this. Every software almost uses this. When you try to think about the functional volumetric differentiation.
I think the drawback is that when doing this, if your, say, nonlinear dynamics is very complicated, you discretize that nonlinear dynamic, then you get something, a nonlinear dynamical system, which is very complex. Now, if you use automatic differentiation, it's like closing your eyes, right? And you get the sensitivity out of it, but you don't really get understanding. This is why, you know, in some fields of computational engineering, they don't like it too much because they say, well, if I use automatic differentiation, I do not know anymore what I'm doing, right? And I prefer to do it the classical way. So I run my algo, I do a small perturbation of some parameter, I run the algo again, and then I compute finite differences. But at this level, I understand it's fantastic, right? It's just a tool of doing the chain rule, but much faster than you, or at least than me.
Yeah, they never make mistake. The human always make mistakes, right? So, okay, going back to editor. So we would like to continue computation. Then what to do is just end the debug mode and keep computing and erase this point. So let's compute up to here. Well, there are so many nice techniques in MATLAB. For example, to run the program, you often click here, right? But just F5 does the same thing. So you know, when you're working with keyboard, just push F5. It's much faster. And also, it's a little different topics. But for example, you want to try to see your command is grammatically okay or not. So then if you highlight some parts and only you want to compute this part is to click, I forgot what to do, control enter, yeah. There are important, many of techniques like this. Oh, no, this one. Oops. Yeah, you highlight this, and yeah, F9, yeah, so. Yeah. This F9, highlight this part and push F9. Then the highlighted part is computed. And this kind of techniques helps you to write code. So anyways, we computed, and let me show you what I get. QN. So EQN is the solution after solving systems of equations. So this EQN is sort of structure. So there are, they show the ddx part and the d theta part. So if you want the inside. If you want to look at the inside, put comma and the dx. Then this is the inside. And you can see, okay, this part is okay, and EQN dot d theta will be like this. It gets quite long, but they never make mistake. And after this, I substituted. So this part is actually this substitution. Okay, this command means substitution. Substitute into this expression or just a replacement. In this expression, replace these guys with this. So by doing this, so this differentiation of theta, okay, for example, this xf will be replaced with x1. So that I'm introducing new state variable. Instead of x by f, it will be x1. Instead of x dot, because this is differentiation, right? So instead of x dot, this will be x2. So by replacing this, I will try to derive the nonlinear system equations. Okay, so, yeah. Okay, yeah. This is to do to take a Jacobian. Yeah. To take a Jacobian matrix.
So now you are discretizing.
No, not yet discretization. Still continuous time.
Okay.
Yeah.
Okay, so you are defining the model in the MATLAB.
Yeah. Still modeling part.
So that you could then maybe launch an ODE solver.
Yeah, later. Yeah.
Okay.
Preparation for ODE. Yes. So, okay. For example, up to here, try to run, and then you get this F showing the vector, which will be the right-hand side of your system. See, first element is x2, which is x dot, and the second element is like this. This is a fraction, and the third element is theta dot, x4, and theta 2 dot equals these guys. And then this is the nonlinear equations. Sometimes when you are writing this kind of script, you want to check this equation is really correct or not. To do that, just write LaTeX, F, and then, no, LaTeX, just a moment. Yeah. Yeah. Then you get this code, and copy this expression and paste into a LaTeX and show equations. Then you can see this computation is what you are expected or not. This can be used to write your thesis, right? It's easy, much easy. But sometimes the order of terms are not as you want, but you need to rearrange the order of terms. But this way you can confirm your computation. Okay, let's go back to the editor. So now we have nonlinear system. Which is in NSYS. And we are going to take Jacobian matrix here, A mat. And let's see what we get. This A mat is still in a symbolic mode. So this is exactly what I showed in the PowerPoint, deriving the A matrix. Still, this is symbolic form. So, in a way, okay, you can still work on this A, but it's better to have numeric data. And in A, it's already numerical. What I did is use double command called double. Double means the double precision number. Before that, this A was sort of symbolic data. Now this A and B are the matrices of your linear system. Okay. Another file, the second file, which is inverted pen model 2, is not necessarily. It's not necessary. I just wanted to automatically write the differential equations. It takes a little bit time to find out how to do that, but as long as you use this way, like our nonlinear system is NSYS, and type out in the command window and copy it in your editor, for example, like this. I will and copy it, and that's the system, nonlinear system. The problem of this expression is that the data understand. The MATLAB doesn't understand this x3 will be the third element of x. This should be x parenthesis 3. X is vector, and the third element should be x parenthesis 3. What I wanted to do in the second file is to automatically replace this x3 with x parenthesis 3. But if you work directly on this using the editor's replacement function, then you don't need to use this second M file. But sometimes if your system is very, very long and the replacement, even the editor replacement could cause error, then it's better to have this kind of automatic replacement. So anyways, this second M file should be skipped. And go to the third M file, which is inverted pen control. Okay. So as I wrote here, first you have to run the first M file. And after this, we compute this. And the LQR control is as simple as like this. So define your R, in this case just one scalar, and Q is the penalty on the states. I take just diagonal matrix, and use CARE. C means continuous time algebraic Riccati equation, ABQ. And then MATLAB will compute the solution, and this is a closed loop eigenvalue. This K means that the gain matrix, K, which is actually R inverse times B transpose P. And this report is about sort of accuracy of the computation. So using this K, I define control function, feedback function, F under bar control. This at mark is very, very convenient. This defines a function of X. So I'm defining a function. The name is F under bar control, which is a function of X, and inside minus K times X. And you don't have to care about the size of matrix. Well, as long as this multiplication can be defined, they understand X will be a vector compatible to the size of K. Okay, so this is the linear feedback control. And this is the system. There are A times X plus B times U. But U is a F under the control of X. So this is the closed loop system. And this left-hand side is the name of the differential equation, I under bar linear, because this is linear control and a linear system. And you define function, this guy, as a function of t and x. You have to write t. Otherwise, this ODE 45 doesn't compute the solution. Because this ODE is function of t, has to be. So at t time, comma x, and define your right-hand side. And this is the span of simulation, so from 0 to 10 seconds. This is initial condition. So first, the cart is 0, cart velocity is 0. The angular of the pendulum is tilted 0.8 radian, not a degree. And velocity, angular velocity is 0. And write like this. Then that's the simulation. Linear simulation. Very simple. Okay, try to see what you get up to here. And here in Workspace, this window is also very useful, so you should always look at this part. This is the Workspace, which means in memory, what kind of computation results are stored. So these blocks stand for functions, and this sort of array or matrix. And after this computation, we have data of computation in state and time. Okay, here state. This is a 161 times 4 matrix. This 164 was chosen automatically by a ODE45. And this 4 means your system is 4-dimensional. So you get this matrix. That's the solution. That's the numeric solution. And T has the same number of row, 161, and 1 times 1. And you write these data, then you get the simulation results, which is in this next script. So I'm going to run, I'm going to run nonlinear simulation. So this is what I wanted to create automatically. But you don't need to do that, just use editor. So in here, it was x3, right? But now x parent is 3. It has to be like this. Otherwise, OD45 doesn't understand these are, the x is a vector of 4-dimensional vector. Okay, so this semicolon is the sort of corresponding each row. Okay, so first element is x2, the second element is long, I don't know where to go, but somewhere here. It can easy to get lost, but anyways, this computation is correct, and this is the nonlinear system. And this is very important. I would like you to do simulation with the model as accurate as possible. In this case, this is the most accurate model, right? Instead of this linear system, because this is linearized, and this information, this completely lost the information of sine or cosine. I will show the difference. So this is the most accurate simulation. So you have to do both simulation based on your design model, which is linear, or based on your physics model, which is nonlinear. Okay, so let's do simulation. So this is what you get. The first figure is the position. And the second one is the angle of pendulum. And I wrote linear and nonlinear both. Small, but the blue is linear and red is nonlinear. The behavior is quite different. And in the second figure, this is the response of angle. Blue one is a linear model. Red one is nonlinear model. And I put a specific number here near the initial condition. This is the sort of limit of successful initial condition for nonlinear system with this linear control. So this would be 1.19 radian. Yep. I just tried many times. Okay. So this will be, you multiply this with between 55 and 60. Then you get a degree. So this will be like a almost 60 degree. So if the pendulum is tilted like 60 degree, with this control you cannot really stabilize it. You can try this by writing here 1.9 and do simulation. Because this is almost unstable, so it takes a little bit of time. Yeah. This is the response of the angle. So it's not really stabilized.
So
But
then what are you doing in that case? What is the angle doing?
well, it's rotating completely.
Yeah, but eventually then it's what?
I don't know.
What are the values?
So this is the angle. So this rotates completely.
Oh, this is the angle. It
Yeah,
goes
yeah.
beyond pi. So
Yeah,
to
yeah,
pi,
yeah.
you go.
Yeah.
I see. Okay. Okay.
So you don't need to care about what is this. This is already unstable.
And this is because you.
Because
the initial configuration was
is
pi.
quite large, and using a nonlinear model. Yeah. Yep. Yep. Mm-hmm. Yeah. Yeah. Mm-hmm. Linear control. In a nonlinear. Yes. 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 Yeah. Yeah. Okay, so this is about LQ control.
Oh, and then the algebraic Riccati equation changes.
Yeah, both are algebraic, but the DRE or CARE. So we use the CARE, but instead you can use LQR as well. But from lots of functions here, you realize that there is no simple finite horizon problem like this. So this kind of simple finite horizon optimal control, you have to solve differential Riccati equation, right? And this is the optimal control. In engineering, this is not very popular because this doesn't guarantee the stability. But sometimes you want to solve this. And to do that, you have to solve this differential Riccati equation. The algebraic Riccati equation is this side is 0, right? And if you solve this p is a function of t, and plug into here, the form is quite similar, but this p is time dependent. And then this is the optimal control for this finite horizon optimal control problem. There are no commands to carry out this control. So I made it by myself. So if I have time, I quickly explain what I did. This is the MATLAB file, inverted pen, underbar dric. differential Riccati. And I'm not going to take too much time. You can easily understand. So this is the system. So linear system A times X plus BU. U here is, this part is based on differential Riccati equation, so finite horizon control. And U under LQ is the one we already computed using algebraic Riccati equation. This is the optimal stabilizing control. This doesn't stabilize, but sometimes you want to try this. To get this U function, you have to solve differential Riccati equation, right? And that is computed up here. Okay, we start with the same Q and R, and I made a function f under bar Ric here. This is a separate function. In your folder, you find this f under bar Ric. What does do this is to compute the differential Riccati equation based on your A and R, or a quadratic term, and Q. So this is the function, f Ric. So the differential equation looks like this. Be careful that there is no minus here. So the time direction is converted. And the difficulty of this equation is that this is a matrix equation, and MATLAB ODE always solve vector differential equation. So from this, from here, I have to get the matrix into vector. So if the matrix is n times n, then your ODE, the vector of ODE is n squared. So you have to do reshape. So reshape X does reshape and also this command, dot command. If you have a n times n matrix, for example this, and put this dot command with parentheses, then you get vector. So vectorize. So if you have 2 times 2, and then write this command, then you get 4-dimensional vector. So, and the reshape is that from this 4 times 4 vector, you get 2 times 2 matrix. So you have to go to a vector and then come back to matrix many times. Therefore, it looks a little complicated, but basically this is solving differential Riccati equation. Okay, so in this part is solving differential Riccati equation. Okay, this capital X is the solution. And you have to use this kind of technique, reshape or vectorization. And let me show the results up to here. So actually, this value is a difference from the solution of algebraic Riccati equation and the differential Riccati equation. I taking subtraction. This is small, not too small, but small means that the differential Riccati equation solution is converging to algebraic Riccati equation. And so, okay, this is CARE, this is the solution K, Riccati solution. This XX is from the solution of differential Riccati equation. I took subtraction and show the result. And if you take a little longer, like a 20, then you get better results. 10 to minus 9, which is very, very close to 0. So you see the solution of differential Riccati equation is converging to the solution of algebraic Riccati equation. Actually, to get this result, you have to I had to set the option up to like this.
So the solver of the differential Riccati equation,
Yeah.
did you choose it yourself or it was automatic?
I just wrote the right-hand side and I throw this into OD45.
Okay.
It's accuracy to quite good, 10 to minus 10, 1 to minus 10. Otherwise, it doesn't really converge. So differential Riccati equation convergence is not that fast to algebraic.
And the time horizon you need to see this convergence is very long? Or
Quite long, yeah. Okay, now I want to construct the controller, this guy. But this P is the solution of the differential Riccati equation. But in MATLAB, these data are only a sample time. Therefore, to plug into this U into our continuous time model, you have to get a continuous function. You have to construct continuous function from the data of P of t. Here I use interpolation. So this was actually what Leontine was looking for. So I'm going to explain here for her. Okay. So yeah, in this part I made an interpolation function so that this gain under t is a function of t, continuous time. To construct this function of t, I needed the data of gain, which is computed by differential Riccati equation, P of t. And I prepare lots of data from PT and throw those data in here, and also throw the time data here. And interpolation 1 computes the value, or predicts the value of your time t based on these two data. That's interpolation, actually linear interpolation. So you have data and you just connect the data by straight lines. Therefore, even without the data, this guy computes sort of prediction value, which is gain under bar t. Then this is continuous time function. Now we can plug this into our continuous time as a function of tx, which is control. So this will be plugged into our system. Here. A times x plus bu here using differential Riccati equation, but this is using interpolation. This is now continuous time. And this is a LQ control. And we can do simulation. And the difference, see the difference. Actually, not too different. These two lines are already at the same place, so you cannot really see the difference. Okay, basically this is it. This is all what I want to say. And now we can talk about homeworks. And first, maybe okay, what to do. Everybody has different dealing with different systems. So the derivation of model can be different each other, right? But try to explain how to get the model and how to put into this framework. And then after that, the rest of it is quite easy. Just use CARE and put simulation. But okay, the important thing is try to do the nonlinear or a full order simulation. Because using just a control model is not very surprising. Of course, it will be successful because you compute it based on that AB model. But plugging into your own system, which may be nonlinear or which could be infinite dimensional, then you never know how your system behaves with this LQ control. That's what we wanted to see. Right? That will be a little bit difficult. So any question? We can discuss. Maybe some people have completely different type of problem, and it's hard to put your problem into this LQ control, LQR.
So this way you solve the optimal control problem. How would you address the problem of controllability, where you have to get to a final target?
Well, I didn't really try that one. I already checked these A and B matrices are controllable. So controllability was guaranteed, but I didn't really design controller from one place to another. I only designed stabilization control or optimal control for a given cost function.
So there is can you check, there is a way of checking automatically the Kalman rank condition if I give you matrices AB?
Yeah.
Okay.
Yeah, in control system toolbox, CTREB or something. only numerically. Yeah.
Penalized, right? You do it through optimal control, right? But there is not, in the toolbox, there are no minators, right? You cannot say, okay, I take the system, AD, and then I give you an initial datum, I give you a final datum, and then the computer will give you
No such function.
No.
You have to construct.
Right.
But they have a Gramian. They have Gramian command. So using Gramian, you can control, you can build.
This is a function that our group could build, right?
Yeah,
So
yeah,
you take a system,
Mhm.
and then you give an initial point, a final point, and then the computer tells you, no, this is impossible, this is not controllable, or it's possible, and then it's the path.
Yeah. Mhm.
So you think this is feasible?
Yeah, it's feasible. Yeah.
David, for tomorrow.
This is simulation.
Well, tomorrow evening.
Huh?
Simulation software is this. You put the system to put the target, initial, the simulation calculate
Simulink, that's it.
Simulink?
yes, but only not focus. A few models.
Okay.
Few more.
You have a parameters and you can tune it.
Yeah, within a given menu of models, right?
Yes, a few models.
So, but that would be very natural to do, right? Because we have been doing this, we have done that actually, right? So in some sense, you take the program you have, our program. But we never thought that this could be kind of a function in a tool, control toolbox that could be complementary to what already exists. But I think it would be very natural to someone that wants to deal with control systems. It's like, in Google, right? You give where you are, where are you going, and Google gives you the path, right?
Yeah.
You can do that for tomorrow? No. For Monday? Okay.
So Jesus, will you explain how to make the web page of the homeworks? Yeah?
Thank you.
Oh, you're welcome. Thank you.
I think you should stay in the bar, no go back.
If you want to magnify, you know how to magnify? There is a sort of command in Windows. It's called a magnify.
I don't know in Mac.
That's Mac. Oh.
This is Mac.
Anyone knows how to magnify the screen so that I just like a
No, but this is other thing.
Okay.
No sé si es un problema que hable en inglés, en español, porque más o menos ya he estado hablando con todos. Si cualquier duda, me preguntas y Humberto traduce. Perfecto, ¿no? Vale. Vale, todos tenéis acceso al Icon Project, the folder of Dropbox. Okay? This seminar I put in this path. Okay? In other topics of the tutorials of the source code. Okay? the idea is joder, cada carpeta de estas, each folder, cada carpeta sea un tutorial en la web. ¿Ok? Cuando Noguro estaba hablando, he creado una carpeta sobre su tema. Es llamado el péndulo invertido. Y simplemente he copiado lo que él ha escrito, pero con este preámbulo, ¿no? Vale. Si se ejecuta esta función, quiere decir, crea el tutorial que se encuentra en el World Packages 99, en el PS02, lee este script y crea ese tutorial. Is this your code? Dime.
¿Qué es lo que estás haciendo ahora? ¿Has cogido todo lo que ha contado Noguro?
El código de el código de MATLAB y lo he publicado en la web directamente.
This is now online.
No, this is in my local computer, but
It's visible online.
it's the same. It's only the copy folder. Noguro
So
can.
basically, you have taken just what he has shown, you have decomposed that in pieces, and you have given a title to each of these sections, say, right?
Yes. Only
Initial, define, Lagrangian, this is something you have written yourself, right?
Yes.
Out of the comments he had, probably,
Mhm.
right? So,
I am only put this Noguro,
right.
date, and title.
Yeah, so this,
The other is the Noguro.
yeah, this is like showing the source text file or the PDF file you get after that text, right? Something like this.
It's very fast to
It's the same
public.
content, you didn't touch.
No.
If there are errors, there are errors, right?
Yes. Yes.
And then the plots, you simply took the plots he has shown, ¿no?
Yes.
Has cogido los plots, los dibujos, las figuras y las has puesto tal cual, ¿no?
Lo hace el script, is automatically. Okay. The idea is the homework of the Noguro sea una entrada del blog. Ok. Entonces, para hacer eso, necesito que copiéis en la carpeta de Daikon Project.
Okay, so now this is important because it's the part that will give you some homework. So let's try to translate this.
Vale.
Okay, so now each of them has to do something.
Okay.
Right? First question, deadline. Deadline, when? For next Monday, it's okay? Next Monday, it's okay?
No.
Monday?
Yep. No, ask them.
No, next Monday is okay? Okay, yes. So now, what is the description of what they have to do? Can you say in Spanish and I try to translate?
La idea está en crear un tutorial sobre la tarea que acaba de dejar Noguro. Entonces, para esto,
Okay, we are trying to build a tutorial out of the, say, the presentation, the material, the methodology that Noguro has introduced you today. So for this,
para esto necesito que copiéis la carpeta de Dropbox en vuestro ordenador. En
you
una,
have to copy the Dropbox folder into your computer. First step. Copy Dropbox folder in your computer. Second step.
second step, necesito que creéis una carpeta con vuestro nombre, con este formato.
you
P000,
Yeah.
el siguiente.
You generate, within that folder, you generate a folder following that kind of notation or acronym style with your name. And this is the folder in which you are going to do your burden, right? And don't erase the folder of the others, okay? Okay? Don't do trash, anti-trash. Forbidden. ¿Vale? No papelera, vaciar papelera, ¿ok?
Vale. Una vez creado, dentro de la carpeta, crearéis un fichero MATLAB que será el principal.
Okay, so once you create your folder, the folder you create has a name, yours, and a goal, whatever you are doing, like control of age-dependent models, you know, Jacobi, for instance. And then once you open the folder, there has to be first the main file. The main file is the MATLAB program, right? Of what you are actually doing.
Vale. Es importante que sea solo uno, porque será ese vuestro contenido, y las demás funciones que creéis deberéis meterlo en la carpeta que se llama Functions, dentro de vuestra carpeta donde estéis trabajando.
Okay, so only one MATLAB file, and then all the other functions go to the function folder. You organize things that way. One MATLAB file, and then all other functions you are using, you are importing, go into a different folder.
Next, necesitamos estos tres datos con este formato.
Yeah, so then the main data of the file, whenever you open the file, you identify the file with title, say age-dependent model, date, so author, Jacobi.
El autor lo estoy poniendo como el primer nombre y el apellido.
Okay.
Que lo busquen
So
a la
you use this kind of way of first name and then initial of family name.
And next you can, luego puedes escribir lo que quieras. Hay que tener en cuenta que para hacer párrafos hay que poner una doble
Okay,
porcentaje.
so use a double percentage symbol to switch from one paragraph to another. So you try to edit your MATLAB file using this kind of style. That you can see in Noguru's example, right?
Sí.
Noguru's example will be available there. So you can simply try to reproduce the same style.
Vale. Si no ponéis el semicolon en la vista,
Yeah.
se ve la variable que contiene. O sea, es importante que si quieres mostrar el valor por cualquier cosa, como aquí, si lo quiero mostrar, es necesario que no se ponga el semicolon. ¿Vale?
Okay. So depending on whether you use this this ending dot comma here, right? This symbol, you will either visualize or not the content of the formula, right? So this is something you can determine, right? But it's important. It's just that as sometimes when we write in text, we are not paying attention, and sometimes in the end of the formula we put a dot, and in some others we forget, and it doesn't really matter, right? Here it does matter. Depending on how you end the formula, it will mean that you will visualize it or not.
En este caso, como solo he copiado el código de Noguru, no tiene demasiadas explicaciones, pero si vamos a un ejemplo distinto,
Okay, so in the case of Noguru's example, it was not really, I mean, Noguru developed this file for this purpose, the class today. It was not really done in order to be used with this other goal of showing it up in the web. So there are not many comments in what Noguru has written. You can put more comments, right?
ese es un
But please, if you copy poetry from Wikipedia, put, you know, the reference, right? We are having problems in Spain with ¿cómo se llama?
la referencia.
Con las tesis de los políticos.
Ah. Vale. Este es un ejemplo. ¿Vale? Necesito que se explique bastante lo que se está haciendo.
This is an example in which you see more text. So that in the end what you are seeing is more like a Wikipedia entry, right? So it's not only pure MATLAB code nicely formatted, but rather now is kind of a readable, nearly say introductory text. You know, this could almost be a text, a short chapter in a book to introduction of mathematical control theory and numerical interpretation.
Vale, si se quiere agregar otro tipo de archivos que no se hayan impreso o lo que sea, se necesita crear una carpeta que se va a llamar extra data. Entonces, en este ejemplo,
Yeah, you can always add an extra data folder. You wanna put there whatever you wish. For instance, in this folder they can put a book. Si quieren poner un libro que ellos están usando, un artículo que han usado,
o una
para
imagen
inspirarse.
o algo que hayan dibujado y que les parece pertinente.
So whatever. So you have done some draft simulations that you want to put there. You can. If you have used some article that you found in the internet that inspired you to write a code that way, you can put it. Whatever.
Y en este caso yo lo utilizo porque he
You
creado
have done a GIF with your simulation. You have done some animation movie. You can put it there, right? All this is extra.
En este caso, yo tengo un GIF que quiero mostrar. Entonces se pone en este formato. ¿Vale? Hay ejemplos. Hay varios ejemplos en las carpetas. En este caso, este es el formato en el que yo coloco este GIF. ¿Vale? Espera. Se me ha colgado el ordenador. Vale, sí. ¿Vale? Y esto está aquí, en extra data.
Okay.
¿Vale? Entonces, si quieren poner GIF, se ponen aquí.
You can put there every movie, every MATLAB simulation, everything you want, you can put it there.
Lo importante es cómo llamarlo, que es este formato, ¿vale? Es poner aquí, extra data y el nombre de lo que tengas.
And then you can refer to this extra data within the main file. So this is like a footnote, right? A footnote is just a comment that doesn't pollute the reading of the main file, but that provides extra information for those that want to see more details.
Vale. Y por último, pues estamos viendo cómo hacer esto, pero en principio metemos las referencias a mano. ¿Vale? Listamos a mano, aunque estoy intentando que sea automático, pero por ahora...
Right now, bibliography has to be entered copy and paste from Google or from Mac reviews, but we don't have any other means right now. It's too late.
Vale. Cuando tengáis...
The number of references will not be that large. I don't think it's a main issue.
Cuando terminéis, recordar que estáis trabajando en vuestro ordenador, tenéis que comprimir vuestra carpeta de trabajo y enviármela a mí, para que yo lo actualice en el Dropbox de verdad.
Okay, so don't forget that you are working within your own computer. So once everything is done, not because you see it there, this is being shared. You have to zip your folder. So it's a matter of security, right? So, if everyone was operating online, this could destabilize who could lose information. So you better work offline, and then you send it. You can use WeTransfer to send the folder to you, or it will go through email.
No, I prefer by GitHub, but okay. I need the accounts and other things. But of this file, me lo pueden enviar por email, mejor.
Okay.
Todavía no todos tienen en cuenta, okay. Así que lo dejo.
So this time if you want, you can send it by email, of course, or next time we will try to make it more automatic through GitHub. I think the team has a question.
contando que... Vale. If you can add image, you put the picture in the extra data folder, okay? In the example average control, you go to folder average control, you can see the extra data folder, and in this is the average control GIF. And to put this, I put this format, okay? Extra data slash, no? Slash average control.gif. And you put in this
Okay, well, probably this time it would be better that you start by something not too complicated. So many of you have already done things, so you have already done them. It's more a matter of, for some of you, it's just a matter of making the presentation of that specific project in this format. That's all, right? You have done computing waves in heterogeneous media, right? So it's just a matter of putting the file in that way. Probably many of you are in that situation. For some others, you are, well, Bellman, you certainly have a lot of experience too, but you have already some projects developed for collective dynamics and many other things. Dominic, I don't know, but you are in different situations. But for those that so far never did it before, that you maybe don't have a MATLAB program already done, I recommend you to first try to talk to others, to use what others have done, not to do again and again, the wheel, is we know all, is just at this, right? So most things are done. Just try to shortcut and add whatever you have to add. For instance, I was thinking in your, age-dependent models, we have all the ingredients. There is an aspect, though, in that model, which is this non-locality, and maybe you have to think of this, right? But it's just 5 lines, right? So try to get focused in the novelty of your program. So, for instance, you are doing free boundary, right? This is your issue. And you are doing, model reduction. Try to focus on this, right? Because otherwise you will spend a lot of time on rewriting what others have written. So ask the others how much they already have. But they have certainly written the AD, what you have seen, the quadratic functional, the conjugate gradients, and the discretization of the Laplacian. If you do a fraction, a Laplacian too, and many, many other things. And then once you have achieved this in a small toy example, you can do more.
Ya para acabar, para la idea final, sería que esto no deja de ser un ejercicio para que ellos mismos elijan sus temas y cuando estén libres o cuando ellos consideren que no han aportado en mucho tiempo, ellos mismos elijan el work que se tengan que hacer, o si no saben, en other topics, y ellos mismos creen su contenido, que ellos son los que más saben qué es lo que están haciendo.
Okay, so this is just what Jesus wants that way, is that you are autonomous, so that now you are doing it under command for Monday, because we are just training, right? But the idea is that once you are trained, you can do this whenever you want from wherever you are. This is like when you edit Wikipedia. You say, well, you have been finishing a paper. For doing this paper, you have done a number of simulations, and you say, okay, let me now put it in this format. This will take you 1 hour more, right? Edit things so that you have the extras here, the functions here, the main file here with a few comments, but it's just 1 more hour, and in this way you put it there, and this will increase our, say, common computational platform.
Vale. Por eso todo.
Okay, so, muchas gracias, Jesús. So then by Monday you send it to Jesus. So Monday noon, Spain time.
Okay.
Okay?